Section 1.8 deals with continuity. It is a rather lengthy section, so I'm going to break this into two parts. This first part, we're going to talk about a lot of definitions and theorems and a few examples. And then the second part is just going to be more additional examples here. So we're going to look at some definitions, kind of like a definition of a limit. There's a formal definition and an informal definition for continuity. So again, at any point to write out all these theorems, pause the video when necessary. So this definition, it says a function f is said to be continuous at x equals c if the following three conditions are met. So the first, and I'm going to simultaneously, or like right after each step, kind of illustrate this with the graph. So the first is that f of c needs to exist. So if I'm looking at some graph here, I've got this x value here, but at c, that's what this is saying, it needs to exist. So I need to have some point showing that an ordered pair here. So f of c needs to exist. The second is saying the limit of f of x as x approaches c also needs to exist. So that means the left-hand limit must equal the right-hand limit. Now, I don't know exactly where this limit is going to be just yet. So right now I'm just saying as I approach c from the left and then from the right, those two values are going to be the same. And what value is that? Our third says that this limit of f of x as x approaches c has to equal f of c. So all that means is as I'm approaching c from the left, my limit here is right here at f of c. Also from the right. So that's what makes it continuous. If I were to trace over this, I would have a nice continuous function. No gaps. I don't have to lift my pencil up, and that's the informal definition. But here's a nice illustration for this. The informal definition is what I just said. A function is continuous if it can be drawn without lifting up your pencil off of your paper. So what I just had here was a nice continuous function. So this would be continuous. However, if I needed to say I have an open endpoint here, then I would have to jump over that. So I would have to lift my pencil up here to continue drawing this. So this would be not continuous, or we would say discontinuous. And we're going to look at types of discontinuity. Again, pause the video to write all of this down. All right, so the first type of discontinuity is something called a removable discontinuity. Right now, if we go through our three item checklist, I would say f of x is discontinuous at x equals 2. If you notice on the graph, we have a hole, kind of what I just indicated with that informal definition. The reason that this would be discontinuous is because f of 2 does not exist. So if I were to look and ask, is this function continuous at x equals 2? We would say no, it is discontinuous at x equals 2. Why? Because f of 2 does not exist. That first requirement right here is not met. F of 2 does not exist. The rest of it doesn't matter. We already met one, or had one requirement that was not met. But now what we could do, kind of like add a piece to this, if we were to write this as a function, we could turn it into a piecewise function. We can remove the discontinuity simply by filling in the hole or assigning a value to 2. So by redefining f at a single number, say 2. So let's say we added this piece, we turned this into a piecewise function, which we're going to practice. F of 2 would equal 1. Now this would be continuous because we filled in the part we have to jump over. We removed the discontinuity. Or instead of just a single value, maybe we could write an entire line, an equation of a line that would just cover over what's there and then cover over the whole as well. So like I said, we're going to look at some examples here. But again, removable discontinuity, we remove the discontinuity by filling in the part that's missing. Second is an infinite discontinuity, and this usually means we have some sort of an asymptote, and I'm just going to draw the asymptote here as the y-axis. And then let's say I have a curve over here. Clearly I have to pick my pencil up if I wanted to draw this other part. So right now I would say f of 0 does not exist, but the limit does. The left-hand limit equals the right-hand limit, which is equal to positive infinity. So again, f of 0 does not exist, so that could fail the first part. Or if f of 0 does exist, let's say it's equal to 1, or it could be equal to any number here, the limit will never equal it, since the limit, if I call this f of x, so this first case would fail, would be enough to say it is not continuous at x equals 0. But if f of 0 was defined, then the third item would not be met. So the limit of f of x as x approaches 0 is not equal to f of 0, because this is equal to a positive infinity and this is equal to 1. So if I did define f of 0, the third statement, that last statement where the limit does exist, but it is not equal to f of 0. So again, we would say discontinuous at x equals 0. And the third type, something called a jump discontinuity. So if it's not connected to the open endpoint, that means I have to jump from one value to another. And the step function here, the greatest integer function, is a great example of this. So in this case, if I went through my steps, let's say I'm looking at f of 1. Well, f of 1 does exist. F of 1 right here is equal to 1, so it does exist. So the first part is good. However, it's the limit. So if I were to look at the limit of f of x as x approaches 1 from the left, and then the limit of f of x as x approaches 1 from the right, what am I looking at here? So as I'm approaching 1 from the left, that's equal to 0. If I'm approaching 1 from the right, that's equal to 1. So the limit of f of x as x approaches 1 does not exist. So here I would say that this function, so f of x, is discontinuous at x equals 1. Now, I just chose one part. This repeats, so it's actually discontinuous for all integer values, but if I were just to ask you, is this function continuous at x equals 1, we would say no. But it's also, so it's discontinuous at x equals, if this continued, we could say -2, -1, 0, 1, 2, and so on in both directions. So at all integer values, at all values x, where x is an integer, it's going to be discontinuous because the limit would not exist. But most of the time, I'm just going to ask you for a specific x value. All right, again, pause the video, copy down this definition. All right, now what this is saying is we're just looking at continuity from one side of a value rather than from both sides. So the limit doesn't always have to exist overall. So a function is continuous from the right at a number a if the limit of f of x as x approaches a from the right is equal to f of a. And f is continuous from the left at a number a if the limit of f of x as x approaches a from the left is equal to f of a. So let's see what this means. Go ahead and, if you didn't already, sketch this graph. Let's take a look at 2. Continuous at x equals 2 right now? No. However, but we could say f of x is continuous from the left at x equals 2 as the limit of f of x as x approaches 2 from the left is equal to f of 2. So as I'm approaching 2 from the left, I'm going right up here, and I'm approaching f of 2, because this would actually give me a 5, and f of 2 is equal to 5. So it is continuous from the left only, not continuous from the right, because if I were to approach 2 from the right, I'm headed down towards here, which is not equal to f of 2. Let's take a look now. Is f continuous at x equals 5? No. However, that's saying from both sides here because it is separated. But we could say that f of x is continuous from the right at x equals 5 as the limit of f of x as x approaches 5 from the right is equal to f of 5. So right here, f of 5 is equal to -1, and as we're approaching 5 from the right, that's also equal to -1. So again, we could just be looking at one-sided limits. As long as the one-sided limit exists and it's equal to f of that certain c value, then we could say, but we have to specify, in this case, continuous from the right, not just continuous overall, just from one side. A couple more theorems to look at. Again, pause the video to write these down. First one here is if f and g are continuous at a and c is a constant, then the following functions are also continuous at a. So this is just taking us back to adding, subtracting, multiplying, dividing our functions. So if I were to add f of x plus g of x, that sum, that result, would also be continuous at a. If I were to subtract, multiply them together, or take a constant and multiply it by f or by g of x. And then if I were to divide, just as long as g of a was not equal to 0. So this is all just saying f of a plus g of a, f of a minus g of a, and so on. All right, this next theorem kind of ties into what I'm going to write after it as well. When we're looking at polynomial functions, any polynomial function, the domain is going to be all real numbers. So most of the time we can point out where the function is discontinuous if we're looking at all over the graph, all the x values from -infinity to infinity. Other times we're going to say our function is continuous just as long as it's on its domain. So we skip over the x values where the graph doesn't even show up. So any polynomial is continuous everywhere because its domain is all real values for x. Therefore, it is continuous on that domain here. So again, we're always going to say our graph or our function could be continuous on its domain. So a lot of times we want to state the domain. Any rational function is also continuous wherever it is defined. Therefore, again, it is continuous on its domain. So just to write out some examples, the following functions are continuous at every number in their domain. If we have polynomial functions, for instance, if I have f of x is equal to 5x cubed minus x squared plus 3x minus 6. Again, this domain is all real numbers, therefore continuous on its domain, which we write out. Or if you state the domain, you could say continuous on its domain. So either way, we just need to identify what the domain is to be able to identify it. If we have a rational function, let's say we have f of x is equal to 1 over x minus 3. Again, we would say its domain is all real numbers except x equals 3. So the domain here is going to be -infinity to 3, and then 3 to infinity. So again, we would say continuous on its domain, and we have the domain listed above. If I asked you where this was discontinuous, you would say discontinuous at x equals 3, and we're going to practice some of those. Next, we have a root function. So to keep it pretty basic, if I have f of x is equal to the square root of x, we know that the domain in this case is going to be all positive values in 0, so from 0 to infinity. And picture the graph of this too. If I were to just graph this, remember it looks like this. So it is continuous as long as I start at 0 and keep going to the right forever. So here we would say continuous on its domain. If I were to ask where it's not continuous, we would say discontinuous where it doesn't even show up. So that would be just from negative infinity up to 0 this way, but I wouldn't include the 0. So if I asked you to identify where this function was discontinuous, you would just say where it doesn't show up, which is the opposite of its domain. And then last type would be a trig function. Now think of like y equals sine x, y equals cosine x. The graphs of those are wave functions that go on forever. So their domain is all real numbers. But let's think of maybe y equals tangent x. Cotangent is going to be very similar. Secant and cosecant, their graphs are also similar because we have asymptotes there. So if you recall from Appendix D, y equals tangent x has asymptotes at like pi over 2, 3 pi over 2, because pi over 2 tangent is undefined. So we would say its domain is pretty much going to be all real numbers except, just abbreviated this way, except where x is equal to pi over 2, and to keep adding, because the period is pi, I'm going to keep adding pi units to the right and then pi units to the left. So I'm just going to say k times pi, where k is an integer. So pi over 2 plus 1 pi, plus 2 pi, plus 3 pi, or plus a negative pi, which is minus 2 pi. So where k is an integer. So we would say that it's continuous on its domain, which is what I just described here. All right, another theorem is if f is continuous at b and the limit of g of x as x approaches a is equal to b, then we would say the limit of f of g of x as x approaches a is equal to f of b, or the limit of f of g of x as x approaches a is equal to f of the limit of g of x as x approaches a, which takes us up here to f of b. Now, most of the time, we're just going to use these theorems to help us reason through an explanation where a graph is continuous or discontinuous. All right, and then another theorem, if g is continuous at a and f is continuous at g of a, then the composite function, which could look like this, which means this, f of g of x, or written this way, f of g of x, is also continuous at a. So we're going to take a look at 4 examples to identify where a function is continuous, discontinuous. If we could identify the type of discontinuity, we'll do that. And then we have one more big theorem at the end for this first part of the section. Sometimes we can sketch a graph if it's easy enough. Other times we just have to figure out the domain of the function. So I first want to talk about where this graph is discontinuous. In other words, what's the problem area here? And right now, looking at this function, I don't want to graph it. Look at the denominator. Right now, we know x cannot equal 2. So we should end up with an asymptote or a hole right there. This graph, this function may simplify, which we're going to take a look at. So if x can't equal 2 right now, we would say discontinuous at x equals 2. But let's figure out the domain then. So the domain here would be all numbers except x equals 2. So that would be negative infinity to 2 joined with 2 to infinity. So we would say f of x is continuous on its domain, which we already have listed right up here. Now to try to simplify this, if I have f of x is equal to, see if we, kind of like with the limit, if we could use algebra here to maybe factor. So we could factor into x minus 2 and then x plus 1 over x minus 2, which gives us x plus 1. So when it simplifies to another function, in this case a line, that actually means we have a hole here right at when x equals 2. So if you go back and you match the types of discontinuity, this would be a removable discontinuity. So we had to simplify this here to help us identify the type. So f of x is continuous on its domain, discontinuous at x equals 2 if we were to look at all the x values. And here we simplified it to a line, which meant at x equals 2, because right now this means f of 2 does not exist. We can provide a point to fill that in, which would remove the discontinuity. All right, for B, we have a piecewise function. And looking at this, it is going to be very simple to graph to help us out. So notice, though, this is just f of x equals 1 over x. So this would graph right here. So right now, and then to fill in this piece, x equals 0, f of x equals 1 when x equals 0. So that would be like a point right here at 1. So we do have that f of 1 does exist because f of 0 rather. So f of 0 is equal to 1. So that works. Now the limit, so I'm just going to say the limit of f of x as x approaches 0 from the left is equal to negative infinity. The limit of f of x as x approaches 0 from the right is equal to positive infinity. So the limit does not exist. So the limit as x approaches 0 of f of x does not exist. So we would say discontinuous at x equals 0. However, if we were to identify the domain is just everywhere but 0, so negative infinity to 0, and then 0 to infinity. So I would say f of x is continuous on its domain. Now, because the limits went towards negative infinity and infinity, I would have an infinite discontinuity. And we could abbreviate. All right, so again, the first item in that definition was true. F of 0 did exist, so that was met, but the limit, that second part, did not work here. So we were able to say it was discontinuous where f of 0 was, or x is equal to 0, because again, we have the limits, the limit just doesn't even exist. And even if it did exist, it would not equal f of 0. All right, this is an example. Again, we don't want to try to graph this. We actually want to sort of separate this into smaller functions. So let's maybe say, let's let g of x just equal x squared. And then f of x could equal sine of x. That way, if I wanted to write out h of x would just become f of g of x. And that would give me this part right here. So going back to that last theorem that I wrote out, if g is continuous at a, well, g of x is continuous everywhere because g of x is just a parabola. So g of x is continuous on this interval, which means everywhere. Therefore, g is continuous at a because a is just any number that falls within this interval. And then we would have f of x is also continuous everywhere because the graph of y equals sine x goes on forever. So f of x is continuous everywhere. Therefore, f of x, actually I want to phrase that backwards to follow the theorem. So I would say f of x is continuous at g of a. Therefore, f is continuous everywhere. Because again, we could say it the other way too, how I started this. F is continuous everywhere, therefore f of x is continuous at g of a. And then ultimately saying, if those two conditions are met, therefore h of x is continuous at A because it's continuous everywhere as well. And again, from negative infinity to infinity. So what we did was we broke down a more complex composition of functions to look at them individually, and then we used that theorem to help us out. So if we could say that a function is continuous everywhere, then we know it's continuous at a certain A value. And then again, vice versa here, we could say f is continuous everywhere, as well as saying f of x is continuous at g of a. Once those two are met, then we know that the composition of their functions is also continuous everywhere and continuous at x equals a. All right, now for this example, we want to take a look at the denominator here. So again, identifying the domain. Now there was a problem on the writing assignment where I just gave you the square root. And when we have a square root in the denominator here, we want to make sure that it does not equal 0, and it has to be positive. So what I want to do is take this x squared minus 7 and say that, well, it can't equal 0, so it has to be positive. So I just want to do this. But in order to figure this out, because it is a quadratic, it'd be easier if it just said x minus 7, then we would be able to figure out that domain. Now for this, I actually want to take some a number line here and figure out, again, this is just a parabola, so we want to know where the parabola is greater than 0. Well, what I'm going to do is first figure out where the parabola crosses the x-axis. So I want to take x squared minus 7, for right now set it equal to 0. So now x squared is going to equal 7, x is going to equal plus or minus radical 7. So if I have 0 up here, I'm going to have radical 7 units to the right, and it's going to cross over here. So these are my two x-intercepts. And imagine that I have a parabola going through this. I'm just not graphing the y-axis. That would go just right here through the middle. So this parabola is greater than 0, sitting above the x-axis. All the y values are greater over here and over here. So this tells me this is not the graph of f of x. This is just helping me figure out the domain of f of x. So the domain will work here if I'm at negative infinity to negative radical 7, and then union with radical 7 to infinity. All right, so here I could say f of x is continuous on its domain. So if I were to graph this, it would only show up from negative infinity to negative radical 7, and then the graph would resume from positive radical 7, keep going over to the right here. I would say f of x is discontinuous in between the radical 7s. So it would be, and actually I would include these because that's what would give me 0. So I'd actually have a bracket, negative radical 7 to radical 7. This is where the graph just doesn't show up, so that's where it's missing, discontinuous there. And we could say that this could be a jump discontinuity because the graph shows up on one side, but not in the middle there, so we'd have to jump from one value to the next. So we're not really going to identify the type here, but know that it definitely has a gap here. It's not a removable discontinuity, but it would just be perhaps a jump discontinuity, or even an infinite discontinuity with what it's graphing. So because we're not looking at the graph of this, but no, because it is rational, we would get those asymptotes. So yes, we're leaning more towards the infinite discontinuity. So we can actually put that down, be an infinite discontinuity, because we would have asymptotes there at negative radical 7 and radical 7. All right, this is actually what I just went over looking at the square root when I identified the polynomial or the root function. So again, if just y is equal to radical x, y is continuous on its domain from 0 to infinity, discontinuous everywhere else from negative infinity to 0. Again, just where it's not showing up. All right, this last theorem is called the intermediate value theorem. and this says, again, pause the video to write this out. Suppose f is continuous on the closed interval from a to b, and we're going to let n be any number between f of a and f of b, where f of a is not equal to f of b, so they have to be at different values. Then there exists a number c in the open interval from a to b such that f of c is equal to n. So we're just going to make a sketch of the graph here. Let's say it looks like this, and there's so many different cases as well. So let's just say I have a to b. This is a closed interval, so I'm just going here, and then I'm going up here. So right over here would be f of a, and then up here would be f of b. What this is saying is I have some value n, which is right in between f of a and f of b. So right in here, I have some value n. Let me just kind of pick it for right here. So just to draw these over, there's my f of b, there's my f of a. So if I were to go over from n and hit the graph again and go down, then this would give me a c value. So c would have to show up between a and b if n, so we have to mark n first. N is between f of b and f of a, so then this would just be equal to f of c. So all this is telling me is there has to be a c value that exists somewhere between a and b such that f of c is equal to n. Now, how else we're going to look at this is if our graph goes below the x-axis, because we're looking for roots or solutions or x-intercepts here. So again, I want to go ahead and draw this graph. And I'm going to go straight down. So here's my closed interval. So one value here, f of a, is actually less than 0, but f of b is greater than 0. So here I'm going to write this out that f of a, or 0, is in between f of a and f of b. So if this is true, then to go from f of a to f of b, I have to cross the x-axis. So then that indicates that I have, let me mark this over here. So here's f of b. So I'm going to call n right here. So n is going to equal 0. So that means if I go over between a and b, I have some value right here at c, so that there has to exist some c between a and b such that f of c, which is equal to n, is going to equal 0. So as long as part of my graph, and the whole graph has to be continuous, if I'm over to the left and I need to move over to the right, so if f of a is below 0 and f of b is above 0, it makes sense as I travel between a and b, I have to cross the x-axis somewhere, and that's what's happening here at f of c. The c value is my x-intercept because f of c, which is equal to this n value, is equal to 0. So we're going to use that on this last example, and in WebAssign, it's going to take you through this long process again, so I want to go through that with you in this example. So we want to show that there is a root or an x-intercept of this equation that shows up between 1 and 2, meaning x equals 1 and x equals 2. All right, so I first want to determine, so this is x equals 1 and x equals 2. So first I want to figure out what f of 1 is. So I just substitute a 1 in here. And we'll calculate this. This just becomes 4 minus 6 plus 3 minus 2, which will give me a negative 1. So right now, f of 1 is less than 0. F of 2, 4 times 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2. So that will give me 8 times 4, giving me 32. 4 times 6, so minus 24 plus 6 minus 2, and I'm going to get a 12. So right now, f of 2 is greater than 0. So now this becomes f of 1 is less than 0, or 0 is in between f of 1 and f of 2. So that means at some point between x equals 1 and x equals 2, I'm going to have an x-intercept. So again, this means there is an x-intercept somewhere in between x equals 1, and x equals 2. And it's going to be a number somewhere in between -1 and 12. So just to write this out, and this is going to be the technical wording in WebAssign that you're going to see. So we're going to say that is n equals 0 is a number between f of 1 and f of 2. And that's what I just said. It's going to be somewhere in between -1 and 12. Now f is continuous, so that was that stipulation. So now f is continuous since it is a polynomial function. So the intermediate value theorem states, I'm just going to abbreviate, the intermediate value theorem states that there is a number c, so that there exists between 1 and 2, and then therefore f of c is going to equal n, which is going to equal 0. So again, it says that is n equals 0 is a number between f of 1 and f of 2. Now since f is continuous because it is a polynomial function, by that intermediate value theorem there exists a number c between 1 and 2 such that f of c is going to equal 0. So again, to rephrase this, this function 4x cubed minus 6x squared plus 3x minus 2 equals 0 has at least one root in the open interval from 1 to 2. Has at least one root or one x-intercept in this open interval from 1 to 2. So we want to be more specific. In this part, we're just going to use a calculator. So let's choose maybe f of 1.2. And I'm just doing this on a calculator. I'm just substituting in 1.2 right up here. And I actually get a negative 0.128, which is less than 0. Let's try f of 1.3. I want to kind of keep them very close together. When I do this, I actually get a positive, so 0.548, so that's greater than 0. So now that tells me my x-intercept is somewhere in between 1.2 and 1.3. So maybe let's try f of 1 point, and you could pick any number slightly above 1.2, so I'm going to try 1.22. So this is actually giving me a negative 0.007008, so I'm still less than 0. Let's try f of 1.23, and here I get a 0.056068, which is greater than 0. So I'm becoming more specific and getting very close here. So we would say, so a root lies in the interval from 1.22 to 1.23. So we were narrowing it down between 1 and 2. That was still kind of broad. So we did 1.2 to maybe 1.3. Now, if you did like 1.2 to 1.5, that would be fine, or 1.1 to 1.7, and then you would want to narrow that down. So a root lies in the interval from 1.22 to 1.23, and we're as close to it as possible. We could take it even further, but that's going to be good enough for now. All right, so again, this is just the first part of section 1.8. I'm going to go over more examples in the second part.